here to celebrate the unity of mathematics, to figure out what all these fields that Dennis Sullivan have been working on through his life, what all of them, starting from quantum field theory and at least fluid dynamics, have in common. So it will be our task. So by the end of this conference, we're supposed to understand at least that much. So let us start with talk by Stanislav Smirnov, who will talk about CFT and SLE. I guess conformal SLE and
Okay, so thanks very much for the introduction and for the invitation. It's a great pleasure and a great honor to open the conference in Dennis's honor, and I'm a great admirer of Dennis. So he, well, there are many papers of his which I really like. So it's like I know that Dennis has this criteria. He likes some theorem and he would like to steal it. So if he has many theorems, I would really want to steal. Meaning that really when you see them and you see the idea and you just think, well, how on earth I haven't thought about this myself. And not only that, he is always willing to share his ideas and talks with people, and I have had a great interaction with him. Actually, it started sort of indirectly because I was writing, I don't know whether Misha remembers, but when I was writing my master thesis in St. Petersburg, we encountered some examples. It was in classical analysis and approximation theory, which were sort of related to dynamical systems, so we needed a consultation. I asked my advisor, Victor Haven, he wrote to Misha Lubitsch, and Misha Lubitsch asked Dennis Sullivan. And Dennis gave answer to Misha Lubitsch, who wrote to Victor Haven, who gave the answer to me. And it sort of kind of clarified that the situation that the world is not all that classical, that there are some dynamical, some of them practical examples, and it led actually to theorem which I like very much. And then what actually happened that my advisor was giving a talk about this theorem, and Dennis went by accident into the room, and he liked this theorem, so it made connection to something else which he was doing. And since then I went to visit Dennis many times, and I think out of, besides my advisors, he is the person who influenced me most, and I learned many things of him, so in a sense, sort of indirectly, you are one of my advisors. And another interesting thing, like all of us know famous Dennis seminars. So it's, I've never seen anything else, anything like that anywhere in the world. It's like, you know, there is this Russian tradition of seminars which run well into midnight. It's like this conference, if you look at the schedule. So in Russia, basically, if you don't run over time, people think that you have nothing interesting to say. I'm just warning you about my talk. In Dennis's seminar, it's even longer, but somehow it's done differently. That Dennis wants all his graduate students and postdocs and everyone understand what's going on, and it's done in a very nice way. And when I first went to visit Dennis, so he invited me and he said, well, I wanted to give a talk about this theorem. I said, well, I'm not interested in that now, I'm interested in this, I want to talk about them. He said, no, you want to give about this because I want to hear it and we argue forever. I said, well, I know that you have a double seminar, maybe I just give 2 talks about this and that. And then there was this silence on the other end of the phone. He said, are you sure you want to do that? And I go, oh, yeah, sure, 2 talks of 1 hour. I mean, are you sure? So finally I ended up giving 1 talk of 5 hours and 1 talk of 3 hours and a half. I'm not sure that I will be ready to repeat this anytime soon. Well, certainly not today, but not in 8 hours. And today, I mean, when I was thinking about the topic, there were several things which are somehow much closer to specific things Dennis did. But then I looked at the title of the conference, which was Geometric and Algebraic Structures, and I decided to talk about an area where geometry and algebra intersect, but still we have to understand their connection better than we currently do. And so the title is Conformal Field Theory and Schramm-Loewner Revolution, or more precisely, I will talk about how they apply to two-dimensional statistical physics. Now, there is the second reason why I've chosen this title. Dennis told me long ago how he came to be studying mathematics, and I checked it yesterday. You know that somehow Riemann is responsible for us not having Dennis the chemical engineer. Because Dennis was studying as a chemical engineer until he went to advanced calculus course, and there was Riemann theorem. And when he saw that there is such a sort of beautiful and geometrical thing, he decided to do mathematics. And this is also a theorem which will play a main role in this talk. So this is what makes what is done in this talk possible. So I will speak about two related subjects, conformal field theory and Schramm-Loewner revolution. Essentially, those are two different ways, one invented by physicists, Wendelin calls them a logic of Hardy and others, and another invented by Oded Schramm, to look more or less at the same thing. And it's a fairly large subject, so I will look at a particular application to two-dimensional lattice models. And there is really a fruitful interaction between geometric and algebraic approaches. So I will start with a simple example. It's a classical model in physics which was proposed by Lenz, who was advisor of Ising, as a model for ferromagnetism. So you look at the covering of a square grid. Well, you can do it in 3 dimensions, but we live in a complex plane. And you think that each square is a small magnet which can have 2 possible orientations. And nearby magnets, they, with some force, try to align, try to be of the same color. So this, with fairly good accuracy, would reproduce what you see in ferromagnetic behavior of iron. Indeed, with very good precision, because what we do here, we count we only look at the interaction between nearest neighbors, and in real life the force of the interaction decays so fast that it's this nearest neighbor, they account for like 97% of the real interaction. So we have to quantify what does it mean that nearby squares tend to be of the same color. So essentially a probability of configuration is x to the power number of pairs of neighbors which are of different colors. So x is a temperature parameter. And what Ising proved in his thesis that there is no phase transition in dimension 1, and Pyros proved that there is a phase transition in dimension 2 and higher. Kramers-Vanier calculated critical value of x in dimension 2. So what does this mean? This means that if you change x, then there are 3 regimes. And there is a critical point, and what is astonishing that the whole interval of x from 0 to critical point has the same frozen regime. So here, you can see it in this rectangle, and in this rectangle we've taken boundary data which are red below the equator and blue above. And if we take x very close to 0, what we specify here that the probability of configuration is some very small number to the power number of red-blue neighbors. So this probability tries to minimize the interface between red and blue. If we take boundary values all red, then essentially it will force us to cover everything in one color, maybe with the small islands like here. But since here we are forced to have an interface which goes along the equator, what happens is that we have one blue half, one red half, and a boundary which tries not to deviate very much. Actually, we know that it deviates like a Brownian bridge, and in the box of size n, it will deviate to the order of square root of n. So this is the frozen phase, and what is astonishing is that you have this phase all the way to the critical temperature. On the other hand, if you take, so this is low temperature phase. If you take x, which is close to 1, then essentially probability is 1 to the power number of something, so probability is always proportional to 1, so all configurations are equally likely, so you just toss a point for every square, and you get something like that. But it turns out so that similar behavior you have not only for x equal 1, but for all the x up to critical temperature, and then there is another critical phase which exhibits some interesting fractals of dimension 5 thirds and so on. So this is what means that there is a phase transition, and there is this phase which is frozen, so there is nothing really interesting happening there at the first glance. And there are these two more interesting phases which exhibit fractal behavior, and they have something to do with conformal invariance and complex analysis. Now, I will maybe say more not about what conformal field theory is, but how physicists arrive at what is conformal field theory. Because it sort of somehow explains how they obtain this intuition, and also it provides some interesting problems for mathematicians. So if you talk to a physicist, he would say that Ising model is exactly solvable, or Ising model is integrable, or Ising model is a free fermion, and we know everything about it. So what does this mean? It means that there are many things about the Ising model which can be calculated exactly. Exactly doesn't always mean rigorously, but many of these calculations are actually rigorous. And there are independent ways, so they start with the famous works by Anzagen, and then Kaufman and Anzagen, and Young and Hansen, Ward, etc., etc. The somehow downside is that only some results are rigorous. There is limited applicability to other models, and also it's not, by far not all the things can be calculated in some reasonably rigorous way. So after all these calculations, several people, so the main players for Cardano, Fisher, and Wilson got Nobel Prize for that. But the first time it appeared in the papers of Peterman and Stuckelberg, a renormalization group theory was proposed, and this is actually what motivated a renormalization group in dynamical systems also. Basically, in a nutshell, what was proposed that if we do some coarse graining, some block spin transformation, then it corresponds to changing the temperature parameter and changing the scale of the model. So we start with the model, so I just copied two illustrations from papers of Michael Fisher. So if we take a model on a square grid, and then what we do, we take blocks 4 by 4 of spins. And then we replace each of them by one spin. So say we take majority. If there are more pluses than minuses, we put plus. If there are more minuses than plus, we put minus. And we get a model on the other lattice, which has a lattice step 4 times more. Of course, we don't exactly get Ising model there, but up to first order approximation we get. And it turns out that there are good conveying arguments which say that if you do this, you should get again the Ising model on square lattice up to first order approximation. Only you should change slightly the temperature and change slightly the scale. So essentially the bottom line is that if you change the scale, if you do some renormalization, then you change the temperature parameter. And then the argument goes that, like in renormalization theory in dynamics, that you get a big parameter space of all the possible Ising models, and it's much bigger than the space, say, of quadratic polynomials, because quadratic polynomials, if you do some straightening, it's x squared plus c, just one parameter. If you do just parabola type maps, again, it's graphs of functions which look like parabolas. Here, element of a space is some Ising model. So element of a space is some random coloring of a plane or some Hamiltonian. So it's really much bigger space, and you should look beyond the nearest neighbor interaction. So it's really huge infinite dimensional space. But you expect, so this is a copy of a picture from Michael Fisher's paper, and some of the caption he had for it. He actually had thrice longer caption for this picture. But what you expect to see that there is this space of Ising models. And if you do renormalization, say you replace 4 by 4 blocks by one point, then it corresponds somehow to jumping from one place to another, to flowing in this space. There are actually different renormalizations you can do, not 4 by 4 or 5 by 5 or something else, but essentially what you expect to see is that the usual picture. There are some fixed points, and there are flow lines, and there are many unimportant fixed points. For example, here for the Ising model, one of the unimportant fixed points is where you cover everything red with probability 1, so it's not very interesting, but well, it corresponds to absolute zero temperature. But there are more interesting fixed points, so the non-interesting fixed points usually will be attracting or repelling, so everything in small neighborhood will be sucked in. So for example, this is what happens with this picture here. There will be also more interesting fixed points where there are attracting directions, there are repelling directions, and this is what happens with the critical temperature for the Ising model. So actually, it's so on the square lattice, as I said, we know exactly critical temperature because of the Krapers-Vanier argument. But normally, it's very hard to model on a computer, because when you take finer and finer lattice, you should be careful to really stay on the path which goes to the critical point. If you don't know exactly the value of the critical temperature, you should somehow make more and more precision and do some tests on each step. Otherwise, you'll just speed off to another direction. So there is this whole picture, and it was never rigorously analyzed, I would say more at the end, so it motivated what happened with the normalization theory for dynamical systems later, but it also motivated the conformal field theory. So the conclusion was that there are important parameters, there are important fixed points, and fixed points corresponds to points where you change the scale and it's the same, and the temperature stays the same. And this is like the critical temperature, and then the argument goes that at this critical temperature you have, in a sense, a limit, some sort of Ising model on lattice with 0 lattice step, so it's a field theory. And it's a massless field theory which is invariant under rescaling, because when you change the lattice step, you still preserve the temperature. So in the limit, this also holds. Conformal field theory is a theory where, besides this, you demand that it's invariant under conformal transformations. Now, for rescaling, even for rescaling, it's not clear why you should have invariance under rescaling. So here the main motivation is that there is this renormalization group theory, but in principle, if you think, well, it might very well be that it's not invariant. On the other hand, if you have a fixed point, it should be invariant under rescaling. Just that by the definition, if everything converges to a fixed point when you rescale, then the fixed point itself is invariant under rescaling. It's a little bit more ambiguous with the conformal transformations because, well, here is an example, very simple exponential transformation. It certainly perturbs the lattice. So as square lattice go to some curvilinear lattice, why it should be the same model if you send mesh to 0. But again, the motivation comes from the renormalization group that somehow when there is some sort of universality, when you send mesh to 0, you should always get the same limit. So historically, what happened is that the first time this arose in another context for Brownian motion, and this is a very well-known example. So the random walk on a square lattice, say, is not conformally invariant. If you map square lattice to another square lattice, it's no longer square lattice, it's curvilinear. But the famous theorem of Paul Lévy says that in the limit you get Brownian motion, which is conformally invariant. So what happens is that if you look at the random walk trajectory where the mesh is fairly small, you won't see much difference on the left and on the right. So it will be already almost conformally invariant. Now, it's a bit more difficult for other models, and historically what happened is that first there were papers by Kadarov, Lashinsky, Pokrovsky, where they just observed that the renormalization group theory suggests that we should have for some limits which are rotational and scale invariant. And they observed that if this is the case, then if we take 2 points and look at the spins there, so one is red or blue and another is red or blue, so let's say ±1, ±1, then the correlation between these 2 spins, the expectation of their product, can be calculated. So you can write the formula for this. There will be still unknown parameter, but you get some sort of power law for the correlation of the 2 things. And the power in this law, it will depend on the model. So for Ising, it will be some power. For another model, it might be different, but at least you have a power law for correlations. And then what happened is that Polyakov postulated Möbius invariance, where it's if you read his paper, there is no specific motivation why it should be Möbius invariant. He just said that there are conformal transformations, and besides rotation and scale change, there is also inversion. And if we postulate also invariance under inversion, then we can calculate 3-point correlations. We can write also formulas for that. And he has no specific reason why it should be true. And also there is some confusion in this paper between conformal transformations and Möbius transformations. Also one has to point out it's sorry?
I'm also confused about that.
Well, Möbius transformations are conformal transformations of the whole plane. So in this paper, in one place it sort of assumed that if you have conformal transformation of a piece of a plane, it can be continued to the whole plane, which is not exactly the case. Well, of course, later he understood it pretty fast. This is actually the case in dimension 3, that if you have conformal transformation in dimension 3, over some small domain, it can be continued to Möbius transformation of the whole space. So there are not so many conformal transformations in dimension 3. And this is one of two reasons why we work in dimension 2. If we would be working with conformal invariance in dimension 3, it wouldn't provide so much information because there are few conformal transformations. But another reason is that many processes are not conformally invariant in dimension 3. So Brownian motion is not invariant under inversion in dimension 3. So so dimension 3 has been attacked in different ways, so there will be some covariance under diffeomorphism, but it's a completely different story. And then the main paper which really led to conformal field theory is a paper of Wendelin Werner, where they really observed that there are more than just Möbius invariants. And the hand waving goes like that if you have invariance at the scale change and rotation, then you should have invariance under all conformal transformations because locally they are just that. It doesn't quite work because there are examples. So John Hardy has counterexamples which come from elasticity theory where this is not the case. So one has to be more careful. But in the sort of framework of the models we are concerned with, like Ising, this generally works. And then it allows to essentially calculate all the correlations. There are nice formulas only up to 4 points, but then you have some recursive formulas. So essentially you can determine everything about your model. And there is only one free parameter left. So in physics usually it's denoted C, so central charge C, but there are different notations with G or kappa in SLE, but there is just one parameter family of formulas, and if you know the parameter you can calculate everything. Then Hardy worked this in the case of the boundary, because essentially in the paper, if the mathematician reads it, there is they speak about all the conformal transformations which map domains onto domains, but they speak of them as if they are defined in the whole plane. So there is some ambiguity there, but so it all resolved in a way which is non-contradictory in the end, but it's not like mathematically correct. So what this leads to is that there is in the end a beautiful algebraic theory which concerns itself with these correlations. So this is the algebraic part. This is completely mathematically rigorous theory. So you can write some conditions which will tell you whether the 2-3 point functions are correlations of some conformal field theory, and then you can study them. It leads to beautiful representation theory. Now, because conformal maps are involved, so I spoke about spin correlations, but essentially everything can be rewritten in terms of correlations of some complex valued things which turn out to be holomorphic. So important role is played by some ODEs which have holomorphic solutions, and then real objects like spin correlations you can rewrite putting the complex conjugate over some of these holomorphic objects. And what is interesting is that it leads to, if you believe in the relation to lattice model, which was the original motivation for introduction of these conformal field theories, then it leads to beautiful predictions. Like, for example, cluster of percolation almost surely has dimension 91/48. But whereas this is a completely rigorous number in algebraic counterpart, so it arises as a weight in some representation of some algebra, the relation to actual lattice model where it would make it's really interesting that you have some fractal dimension 91/48 for over a long time was missed. And well, here maybe I just want to mention that there are several different methods which imply conformal invariance, but don't go into this Wendelin-Werner role. But again, it's the same, that there is a beautiful algebraic theory, but the geometrical analytical part is missing. Now I'm coming to the second part, which is the Schramm-Loewner revolution and other things. So recently there was a big progress in mathematics. Here the interesting thing that it started as a geometric and analytical progress, and now people are trying to do the algebraic part. But it was originally motivated by these algebraic things which come from conformal field theory. Of course, if as a mathematician you see a prediction that something has dimension 91/48, it's very tempting to try to prove it and obtain this number in some simple way. Well, you can't obtain it in a simple way, but just to understand where it comes from. And essentially there are two different approaches. One, two different breakthroughs which came. One is with the Schramm-Loewner revolution. It's a geometric description of scaling limits of conformal field theories as you wish. And the other is of discretization of complex analysis to work with a sort of try to work with conformal field theory on a lattice. This actually, I just want to say that mainly we deal with the linear discretizations. There is this non-linear discretization with so-called patterns in which Dennis was involved. And it fits in this picture, but we are not there yet. So it leads to some very interesting discretizations of total lattices, etc., but we are not there yet. So we are trying, but not there yet. And now there is an interaction between this and the conformal field theory. So I want to say in a few words what is the Schramm-Loewner revolution and how it happened to be. So it started with a paper of Langlands with two authors, Puyot and Sandoval, and some papers of his own, which was a numerical study of how you can formulate rigorously that there is a conformal field theory. So he looked at the percolation, which is just the Ising model for x equal 1. So you take pictures like that, say, on hexagonal lattice, you toss a coin for every hexagon, cover it in two covers, and you ask whether there is a scaling limit, whether it's conformal invariant like physicists proposed, whether it's universal, that is independent of the lattice concern. And he did some numerical predictions which somehow pointed out these three conjectures were correct. Now, of course, it's difficult to work with the covering of the plane, so he simplified the thing. So he worked with the probability that there is a crossing. Probability that if you put liquid on top and you look at it as a yellow rock with white holes, then the liquid passes through. So here, for example, what happens for these two particular pictures, in both of these cases, the liquid can go through. So we look at the probability of this event. And this for each rectangle, for each rectangular shape, gives you a number. So what numerically Langlands and company numerically observed, that there is a limit of this number if mesh of the lattice goes to 0. This limit is independent of the original lattice you start with, if you do in the critical class. And it is conformally invariant, so it only depends on conformal models of the domain. Now, what happened immediately is that when this was taught to physicists, John Hardy immediately observed that he can write a specific formula for this limit. So what he did, he put 4 points, and we look at the probability that there is a crossing, and then he started moving one of the points on the boundary of the domain. This changes the probability of a crossing. And it turns out that not only the probability that there is a crossing, but also its derivative have some physical meaning. So he got a differential equation on this probability of a crossing, which is a very simple, it's a type of Riccati equation. So it's like f prime is equal to f squared, this type of sort of thing. But it's basically the simplest nonlinear equation where you have, which is not solvable in algebraic function. So the solution is a hypergeometric function, so it's this 2f1. And what the gamma functions in front, they are for normalization purposes, because probability when you move the point should change from 0 to 1. And then Leonard Harrison immediately observed that the formula simplifies for equilateral triangles, because if you did your complex analysis course, then the Schwarz-Christoffel mapping for rectangles is also given by hypergeometric function. And the angles of the triangle to which you map are given by numbers which are there, 1/3, 2/3, 4/3. So the angles of the triangle will be 60 degrees, 60 degrees, and 60. So the slopes of the lines will be 0, then 120, then 240. And for the equilateral triangle, it becomes really simple. And these two observations, this numerical thing of Langlands, Puyot, and Saint-Aubin, and this observation by Leonard, they led many mathematicians to being interested in this, because you speak not about random covering of a plane, which is a devilish object and difficult to even define, and you speak not about some ill-defined relation between lattice models and correlation functions, but there is a very specific question. What happens with the probability that there is a blue path when mesh of the lattice goes to 0, and there is a conjecture that it has a nice limit. And this led to essentially two advances. And the first one was by Oded Schramm. He suggested to look at something intermediate, not the full conformal field theory, and not just the crossing probability. The crossing probability is just one number, it's not enough if you even prove it. What do you do next? The full conformal field theory is too deep. So he proposed to look at this cluster, or rather at its boundary, which is just a curve. So this is a slide from his first talk about this. And he does the percolation in a full plane. And he covers the boundary white to the right of the origin and gray to the left of the origin. If you do Ising model, this would be important for for boundary conditions. For percolation, it's not for boundary conditions, it's just for the defining the curve which comes next, because for percolation there is no interaction. And then you put an ant on this lattice, who starts exploring the boundary between gray and white cluster. And this ant, it moves using the left-hand rule, always turning between white and gray. And then eventually he goes off to infinity. So is it clear what is going on? So this gives you for each discrete picture a curve which goes from 0 to infinity. Or you can do it in an arbitrary domain, and this will give you a curve which goes between two fixed boundary points. You just cover the arcs between them, one white and one gray. And then what you do, you send the mesh of the lattice to 0. So you have a random curve on the lattice. In the limit, if you assume that there is a limit, there is a random curve, which is a continuum random curve. And you can ask how to describe it. So the physics tells us that there should be a conformally invariant curve. And there is only one parameter family of such random curves. And this is what Schramm proved, and this is actually one of the theorems I would like to steal. But the proof is really very short, it's just 2 paragraphs. And the main thing is to which tool to invoke. So he invoked the two of Lawler revolutions. And actually, the thing is that he saw Lawler revolutions before, but he forgot that he invented them up, or maybe it existed somehow on the level of subconscious, and then he thought, no, I must have seen them, and then he turned to the papers of Lawler. So Lawler invented them to prove Bieber-Bach's conjecture, which was eventually proved by the branch using Lawler revolution. And the conjecture says that if there is a conformal map of a disk to some domain, and you write it as a power series, then nth coefficient is no more than n times the first coefficient. And this is obtained for the Kerber map of a disk to a plane with a slit. The Lawler evolution, it describes how this map changes if you have drawn a slit through your domain. So in the half-plane case, what you do, you start with the half-plane. You start drawing a curve, and you parameterize it by time t. At the time t, you have plane, half-plane, minus a curve. And you write map gt, which opens up the slit, which maps it conformally to a full half-plane. And then you just write an expansion. So there are a few parameters to fix. So because it's defined up to Möbius transformation of half-plane, so usually you fix them so that infinity goes to infinity. Derivative at infinity is equal to 1. And then the tip of the curve goes to 0. And then the Lawler theorem says that if you have a curve, then this map GT satisfies the following equation. GT of z plus WT is equal to 2 over GT of z. So WT is just the first coefficient, just the first coefficient after z, which is there. So if you know the first coefficient, you can completely reconstruct your curve by solving a very simple but nonlinear equation. Since it's not linear, it's difficult to integrate, so if I give you WT, you won't be able normally to get a formula for your map, apart from integral presentation. But it's still important that just one parameter is enough to reconstruct the whole curve. So on an intuitive level, it just means that your curve is drawn with some constant speed. So it's like driving an automobile with a constant speed of 55 miles. In this case, it's 55 miles in conformal metric. So it's conformal speed of 55 miles per hour. And then WT tells you how to turn the steering wheel. If WT increases, you turn it to the right. So you turn right. If it decreases, you turn it to the left. And what happens if you put a random WT? Then you get a random curve. Or if you have a random curve, it's described by random WT. Sorry? Yeah? Yeah. Well, I mean, so for example, if you are driving home after a dinner at a restaurant, if you had some alcohol, then you have WT, which is rather random, and you wiggle the wheel, and you get a random curve. And the more you drink, the more random it becomes, and the more wiggly it becomes. And this is the Schramm's proposition. I mean, not to drink and drive, but to put a wiggly WT. So if you just ask, well, I mean, we want to put a random WT, what would we put there? Well, the answer, of course, Brownian motion. If you just reason like that, actually there were people before Schramm who reasoned like that, and they put it in and say, well, we have some fractal curve, and that's it. So we'll come in a minute how he decided to put it. But even if you just put it out of curiosity, you get an interesting family of fractal curves, which are more fractal the bigger is the value kappa, because the more wiggly it is. And you can just study this family without a relation even to conformal field theory, though it is conformal field theory. So for example, it's almost surely a simple curve. this curve up to kappa equal 4 is simple. From kappa equal 4 to 8, it's self-touching, so it's trajectory which can touch itself, but it never goes through because we define it with conformal maps. And from kappa 8 and bigger, it's a space-filling curve. So this is a very good picture of space-filling curve, but you don't see how the curve went. I will show you later how it went. And then, because the dimension of this curve is almost surely 1 plus kappa over 8, then there are some non-trivial duality relations. So if you take, for example, kappa equal 2 and kappa equal 8, then kappa equal 2 will be boundary of kappa equal 8 curve. And the interesting thing is that in conformal field theory, the calculations of different numbers, they were related to some algebraic theory of representation of algebra. So here, calculations of such numbers, which are essentially the same numbers, they are related to eta couples. Because we are no longer working in the plane. We are working with the real valued function Wt. And if you ask a question, what is the distance of a point to this curve, and you write in terms of Wt, you end up with a question that you solve some system of equations, because there are two coordinates, there will be two equations. And you ask, what is the probability that two equations driven by Brownian motion will produce a parameter which come epsilon close to 0 within 1 hour? So it's a basic exercise you solve in financial mathematics course when you study this approximation of financial markets about Brownian motion. So really, literally, things you teach students or you are taught if you take financial mathematics course. So it's just one-dimensional eta calculus, so really it's very accessible, and essentially it's the same as getting the eigenvalues of some heat-type equations in some domains. Now, what is the relation to lattice models, and why Schramm decided to put Brownian motion there? Not, of course, of idle curiosity, but because he assumed that the physicists are correct, and he assumed that these interfaces, they indeed have scaling limits. So what do we get if interfaces have the scaling limits? Well, we get two things. First thing which we get, which is written here as a domain Markov property, we get automatically for percolation or Ising model, and it says that if you draw your curve up to some time and you know how it went up to this time, then from now on it's the same as if you would just be working in the domain with the corresponding slit. So your curve doesn't distinguish its path from the boundary of the domain. You remember this ant who is going on the lattice. To go on the lattice, for him, it's only needed to know, he only needs to know what is on the left and the right. So to traverse this trajectory, he only needs to cover its immediate neighbor. And he covers...
So you're using the Renormalization theorem?
Yes, yeah. Yeah, this is the theorem which has two important applications. One is Schramm-Loewner revolution, and the other is bringing you to mathematics. So, the other thing is that we know conformal invariance. Well, we don't know it, but we know that physicists teach us that it should be there, and we believe physicists, they are very smart people, they taught mathematicians many things. So if you believe conformal invariance, then if you define curve on some domain, and then you map it to another domain, and then you separately divide it in the second domain, you should get the same curve. So what we do, we combine these two. We draw a curve up to some time, and then we open this slit, and we say that it's the same. So this is basically what it happens here, and this is essentially, this slide is the whole proof. It's, I put the formula because essentially what is done here is the whole proof of the Schramm-Loewner lemma, which says that if we believe that there is a scaling limit of the curve, which has this Markov property, and it has conformal invariance, and you describe it by Loewner revolution, it will be driven by Brownian motion, with some unknowns y. Because we just write that gt plus s, given gt, is the same as composition of gt and js. Why? Because we just drive it, open, and it's always when you open, you map to the same domain. So it's like Brownian motion, you can look at it as a random walk. You take one step, then independent another step, and here it's like a random walk in the space of conformal maps. You draw a slit, according to some law up to 1 second, open up, you're again back in the half plane. Again, you use the same law, again. So you compose the same steps, but they are composed as a conformal maps. So the result you see is a little bit more intriguing, but indeed it's the same sort of Gaussian behavior that you iterate the same random walk. So Schramm-Loewner revolution is the random walk on the space of conformal maps. And if you compose conformal maps, this first coefficient, which was important, Wt, it is additive. So essentially you get that Wt plus S minus WT is the same as WS. So you get a process which has independent, identically distributed increments. It's continuous because Lawler teaches us that if you describe a curve by a process, it has to be continuous. That's you use lemma from the Lawler paper. So it has to be brought in motion with some drift, and drifting is excluded because usually we deal with the symmetric pictures that you can exchange gray and white. So this is one of the lemmas which really it's somehow hidden in the original paper of Schramm because the paper is 80 pages, there are many more, but there is this lemma which is really great. And now if you manage to relate some model to this, you have eta calculus to calculate the numbers. Now these are examples for which it is known what the curve is. So percolation tends to SLE 6, and this is a curve which has dimension 1 plus 6 over 8. It has dimension 7 quarters. Now, boundary of uniform spanning tree, so you take a square lattice, say 10 by 10, and you cut the edges so that it becomes a tree. And you take all trees with the same probability, so it's called uniform spanning tree. And then if you take curve which goes around it, it's a Peano curve because it visits every side. So in the limit, it's a Peano curve given by SLE A, which is conformally invariant and has dimension 1 plus 8 over 8 equal to 2. Well, naturally, because it's a Peano curve. There are other examples. So, for example, the Ising model, if you take boundary between two spin clusters, then it is SLE 3, it has dimension 1 plus, so it has dimension 1 plus 3/8, 11 over 8. And there is some sort of percolation type representation of Ising model. I haven't drawn here the cluster because then it's a mess. But you get another curve which is no longer simple, it bumps into itself, and it has dimension 5/3. So this is there to join theories with Dimitrov. Now, if we relate a model, then we can use this whole machine. But the question is how to relate a model. And indeed, there are still many open questions. So, for example, this is one thing with which it is started. Oded Schramm and Werner, they proved that if you take a Brownian motion, so this is a Brownian motion, and you take its outer boundary, it will be the same as SLE 8/3. And then it opens a road to prove that its dimension is 4/3, which was famously conjectured by Benoit. What I proved is that if you take percolation clusters, like the ones we've seen, its outer boundary is also SLE 8/3, so it's again dimension 4/3, because we can calculate with SLE. But also it's conjectured for the so-called self-avoiding walk, where you take all walks on a lattice, so it's like random walk, but conditioned not to intersect itself. So you take all walks of length n with equal probability, but they're not allowed to touch themselves. And this is no longer a Markov process because it's not sufficient to know where you are, you need to keep track of the whole trajectory, and it's more difficult to analyze, so this we don't know. So there are many things which we still don't know, so how we proved some convergence for things for which we know. Basically, what we do, we find some observable, kind of like crossing probability or spin correlation, and we prove that it satisfies some condition for discrete analyticity or discrete harmonicity. So we find on a lattice some object which is discrete harmonic. It's somehow more classical, everyone knows discrete harmonic function is a function on a lattice which has mean value property. Value at a point is the mean of its neighbors. Or some maybe less known discretizations of Cauchy-Riemann equations. Now if you prove it on a lattice, then in the limit it will be just normal harmonic function. And if you know boundary values, then in the limit is a conformally invariant harmonic function with given boundary values. And what you can do from this, first you already obtained one parameter of your model which is conformally invariant. And it turns out that there are two ways to use it. One way to use it is to prove convergence to SLE. It turns out that SLE, you remember, is defined only by driving force. If you can track one parameter, you can reconstruct your driving force. Because if you can probe one function, for example, how far you are from given point, then you can reconstruct the whole driving trajectory. Just by probing this every second, you reconstruct it second by second. So it turns out that if you can do it just for one observable, you already are forced to be in a SLE class. So actually the lemma of Schramm is even better. So his lemma was that if your curve is conformally invariant, random curve with Markov property, it has to be SLE. So the better version of the lemma, if there is a curve, random curve with Markov property, and it has one conformally invariant parameter, say crossing probability or something or some correlation with some point, then it has to be SLE. But the other thing is that you can use it without convergence to SLE, because if you are after this discrete parameter, it doesn't give you an exact formula for the discrete parameter, but it tells you that in the limit when mesh is very small, it's very close to the continuum harmonic function and its parameters. So what you do that up to some small error, which is a function of lattice step, it's related to usual harmonic functions and can be expressed exactly by Riemann mapping to disk, calculating there and mapping back. So this has been done to a number of models. So there is classical work about random walk, so it dates back to Kurn, Friedrichs, and Levy, and then it was done by Kami for diamond model and uniform spanning tree, and for percolation by myself, and for Ising model and for uniform spanning tree again. And the interesting thing that most observable so far, they're actually things which come from conformal field theory. So you should work, if you want to observe with which it's nice to work, is conformal field theory. A couple of them, they are actually from conformal field theory, but weren't considered by physicists before. So mathematics start considering them, and then physicists say, aha, these are actually good things to put in the physics considerations. But generally, it's just the same scheme. Now, I wanted to give it then a couple of examples how it is used. So one example is what you can do for the Ising model. So again, physicists say that we know everything about the Ising model. So this example, what can be done for the Ising model, which physicists didn't know. So, what we consider is an Ising model with the two branching points. So they're, say, here in this picture. And so normally the Ising model is a picture like I've shown, these islands, and the probability of configuration is the x to the power perimeter of these islands. Now we put 2 points which are here and a bit higher there, where you have a branch. So besides these loops, there is an interface running between these 2 points. So it's like Ising, so physicists will say that those are 2 disorder operators. So those are 2 monodromy points. If you walk around this point, red becomes blue and blue becomes red. If you walk another time, then again everything returns to its count. So it's like a point at which if you walk around it, your value changes to the negative of itself. And then when you walk another time, it again changes back. So it can be expressed as the spin model on a 2-fold covering. You take a 2-fold covering, a Riemann surface, where there are 2 square root branching points. And then you say that the model on 2 sheets should be 2 spins, should be negative of each other. So it turns out that if we calculate the partition function for this model, and we put some complex weight, which depends on how many turns this curve, this interface makes between these 2 points, it turns out that we arrive at a function of these 2 points, which is discrete analytic in both of them. So it's a function f of x and y, 2 points x and y, which is discrete analytic in both of them. And it also turns out that it satisfies Riemann-Hilbert boundary values. Why? So Riemann-Hilbert, actually Riemann in this case, it means that in this particular case, on the boundary, it's proportional to square root of tangent vector. Why would we get proportional to tangent vector and to square root? Because we put some complex weight which depends on how many turns your curve makes. And when you hit the boundary, you know how many turns it makes, because boundary can approach only from one direction. So this function we get, auxiliary function, in the limit, it's basically the Green's function with the Riemann-Hilbert boundary data, which you can calculate exactly. Just map to a disk, make 2 punctures at 0 and a point, and you calculate it exactly. So we can calculate it exactly, but then we can fuse these 2 points.
What do you mean by the Riemann-Hilbert boundary value?
Well, it's actually a Riemann boundary value problem in this case, that the function is proportional to square root of tangent vector. So its argument is well defined. So Riemann-Hilbert is usually that you have a function a on a boundary, so that f minus a is proportional to something. So f minus a proportional to b is Riemann-Hilbert. If you don't have a, just f proportional to b, it's Riemann. It's a homogeneous case. So Riemann had it in his paper where he studied the tiles. So he took the cross-section and studied the surface of the tiles, and he had this boundary value problem in PDEs. Sorry?
What kind of boundary?
Any. Yeah, that's another difference with physicists. So physicists can do, so it's if you look at the work of McCoy and Wu and Polymer, for them it's not a problem to prove this. So when we send them their paper, they wrote how to do this in half plane. So they can do this in half plane. But we can do in any domain because we can do conformal maps.
Can you do it in wedges?
Yes, yeah, we can do any fractal, anything, because any domain which can be mapped on a disk. Well, well, not any. Well, okay, the other 2 domains we also can do. but the formula is slightly different. And if you take these 2 points and if you fuse them, then what we had? We had an interface which was running from A to B. If they are nearest neighbors, there is an interface which is running between them. If we insert one edge, we get a loop. So if we fuse them, we get a probability that there is a loop passing through a point. We get a probability that nearby squares are of different color. This is what is called energy function, because the energy of the model will count how many different squares nearest neighbors of different colors are there. So what we can get this expectation for 2 nearby vertices, U and V, of the product of their spins. So it's a product of their spins is 1 when they are of the same color, minus 1 if they are different. Now what physicists knew? They knew that its first term is 1 over square root of 2. This is Kramer-Svanier statement about critical temperature. Then they knew that the next term should be of order epsilon, which is step of the lattice, and it should be conformally covariant. And if you have a domain and 1 point inside, and you have conformal covariant, it can be only the conformal radius of the domain. You map it to a disk, this point to the origin, and the derivative, which maps it to the origin, is this conformal covariant. But the constant in front wasn't known to physicists, so what we do, we can do the constant in front. If it's all red boundary data, it's plus. If it's free boundary data, it's minus. And the constant is 1 over pi. And also it's rigorous. So this is one example of what can be done. Another example is, I mentioned the self-avoiding clock, which counts how many curves we have there. So this model was actually proposed by a chemist. So maybe you could have followed his footsteps. So Paul Fleury, he is a Nobel Prize in chemistry. He has a famous book on chemistry of polymers, published in 1948. And then he asked a question: if you look at polymer, these are actually actual photographs with atomic force microscope of polymers. They're of course not straight lines. I mean, your DNA is not a straight line in your body. I mean, if it will pop out if it would have been a straight line, because it's actually quite long. So, of course, chemistry depends on how it is positioned. And this is actually the question which is way beyond understanding of mathematicians today. We should really work with biologists and chemists on this, because it's way beyond the statistical physics we discuss here. Because normally the molecules you have, like DNA, there are chains, there are links of different type and chains. Some attract, some repel. And what we really see from the experiments, for example, DNA can be knotted. And there is a special proteins which are knotted, which allow it to pass through itself so that it can replicate. So there is a whole branch of biology or chemistry where there are interesting problems for us, which so far are beyond our grasp. But the simple problem he posed: if you take a polymer molecule which has chains, links of exactly the same type, and it's just like thrown randomly in a plane, how would it look like? So he conjectured that the fractal dimension of this curve is 4/3. And this is what led Mandelbrot to conjecture 4/3 for the boundary of Brownian motion, because he saw that the curves are the same. I mean, he could see with naked eye. He knew all the curves by name, and he saw that this is the curve he already met. And the argument which Fleury had for 4/3, it was actually wrong. He used the Landau mean field theory, and then another chemist, famous chemist Dejean, proved that the argument is wrong. But the answer is correct. So he loses something in one place, he gains something in another place, by coincidence the same. In dimension 3 he had conjecture 5/3. It is wrong, but within 2%, and we don't know the correct answer. So lately it was physically explained by Nienhaus, and then physically explained by Lawler, Schramm-Loewner. So they have a paper, it's a mathematical paper, but it says that making conformal invariance for assumption for this curve, we explained this 4/3. Now what we can do, that's sort of the last theorem I want to quote, we cannot prove yet this 4/3. But we can count how many curves they are. So Nienhaus' prediction was that the number of the curves grows like mu to the power n times n to the power 11/32. Now it's very easy to show that it will grow like mu to the power n, because if you have a simple curve of length n plus k, if you cut it into curve of length n and length k, both of them are simple. But if you glue two simple curves, not necessarily get a simple curve, it might self-intersect. So it's clear that there is some concavity involved, and it's easy to see that the number of curves of length n grows like mu to the power n. And mu is depending on the lattice. So mu is not physically, it's parameter like boiling temperature of a liquid, which is different for different liquids. But if you look deeper how the phase transition goes, the next parameter is universal, n to the power 11/32. And the other prediction he made is that on hexagonal lattice, mu is square root of 2 plus square root of... Sorry?
Don't you want to get a smaller number than mu at the end by your argument at an intersection?
No, it just means that mu is smaller than 3, for example. So, for example, what happens on hexagonal lattice, each time when you arrive, you cannot backtrack. There are two possibilities, you turn left or right. So mu is at most 2, because there are no more than 2 possibilities. But if, for example, you start walking in this direction, and next time you turn left or right, then again you walk one step in this direction, again you turn left or right, you never self-intersect. So mu is at least square root of 2. Actually, with a little bit more work, you get that mu is at least golden ratio, and so it's clear that it is exponential. Yeah, you don't kill. And the power law is this renormalization group Lawler teaches us that there are power laws. So Nienhaus has some he had some physical arguments to this effect. So what we proved is that mu is indeed square root of 2 plus square root of 2. So what we do the partition function. So we count f of 0, the number of self-avoiding walks from 0 to z. And normally you would weight it x to the power length and try to observe something special for x equal to square root of 2 plus square root of 2. That below this number the series is convergent, and above this number the series is divergent. So what we do instead, we put a complex weight in front with a complex parameter lambda which counts the number of turns you make. You get a complex valued function, and we prove that there is specific value of lambda, and for this specific value of x reciprocal of square root of 2 plus square root of 2, this function turns out to be almost discrete analytic. Unfortunately, we can only show half discrete analytic. It satisfies Cauchy-Riemann equations. Okay, so in this case, we don't prove that we prove that it's divergence-free. So it's a vector field which is divergence-free. If we manage to prove that it's curve-free, it will be discrete analytic, it would be uniquely determined by boundary values, and we would prove convergence to SLE, 11/30 seconds, 4 thirds, etc., and we would be very happy. But so far we can only show that it's half discrete analytic, meaning that it's divergence-free. Because analytic function is a vector, if you look at it as a vector field, two Cauchy-Riemann equations say that it's divergence-free and curve-free. Or like if you look at it as a form, it's d and delta of it vanish. So here we can prove half of it. It gives some global information, and it shows that something special happens for this value of x for this function. And then we somehow work harder to get lambda away, and it works. It's a very short paper. It's just like 9 pages long, so it's not that deep. So here I come to the end of my talk, essentially it's very interesting to look at this subject, because there is sort of two subjects, both conformal field theory and Schramm-Loewner evolution, were essentially motivated by 2D lattice models, but they are interesting in their own right. And SLE was much motivated by CFT, but now there is a two-way interaction. And it's also interaction between algebraic ideas and geometric ideas. So one thing which we don't really understand is how the algebraic part is holding up. So one example I mentioned is correlations. So for CFT, I said that we arrive at the sort of conjecture or principle that the correlations should be conformally invariant, which allows to classify. So essentially the way it's done, you prove that correlations, they satisfy certain IDEs, certain analytic ordinary differential equations. And the way it's done, you don't apply immediately conformal map on a globus, you apply infinitesimal conformal map. So it's identity plus some analytic vector field. And this is why you have to be careful about boundary, because locally it will be conformal map, but you should be careful that there are no branch points, etc. That there are no critical points. And you get some ODEs for correlations. Nice analytic ODEs which can be solved, and you get what the correlations are. Now if you do SLE, what happens, you have put points in half plane and you start growing, and these points, they flow under the Lawler flow, and this gives you PDEs because there is invariance under the Lawler flow. And these two PDEs which you get, or ODEs which you get for Schramm-Loewner conformal field theory, they are different, fundamentally different, but they have the same solution. And we don't understand why. So it's, for a simple one, if you have just one point correlation function, you can just rewrite by hands and you see that it's the same. But for anything more complicated, we don't know. It's even more embarrassing. If you take SLE for percolation, if you draw it from A to B or from B to A, it's the same curve. But you get different PDEs. So the solution is the same, whereas PD is different, and we can prove that solution is the same. It's, well, we know that it's the same if we know relation to percolation, but for the SLE itself, we can prove that the solution is the same. So there is some hidden algebraic structure which geometry uncovered, which would be very nice to understand. It has something probably to do with integrable systems. So, for example, heat equations which you have there, they usually have a singularity near the tip where you grow SLE. And there some sort of Frobenius theory applies that you get power series expansions with fractional powers which work very well. But there is no, I mean, it's very well known for analytic functions, and here it's not analytic functions, it's functions of two real variables in half plane, so it's slightly different. And the really big problem would be to make rigorous renormalization arguments. So have we advanced with the SLE towards that? Not really, but what we can do now with the SLE a bit better than with conformal field theory, we can describe the fixed point much better in a more geometric way. And maybe this will help this to build this renormalization theory, but I somehow suspect that it will be more difficult than in dynamical systems, and in dynamical systems it has taken how many years? For quadratic polynomials, 30 years? About 15. No, but I say from Feigenbaum all the way to, you guys should know better. Yeah, so, okay, if it's 15 years, then it's more optimistic. Okay, like 15 more years. Okay, so thank you very much for coming. Thank you, Dennis, for being with us all the time, and happy birthday. Status of delay. Okay, I think I even had a picture of it. No, I didn't. So diffusion limited aggregation. So it's a thing. I can show you a picture. What is the status of DLA in this diffusion? It's another three-letter abbreviation. I can let me just think. I probably have a picture of it somewhere. Just a second. Picture of DLA, but wait a second, we have internet here, yeah. So DLA, so let's say DLA applet. We do Google, and there is no connection, of course. Well, okay, I will turn it off. So DLA is a very simple model where you take one particle, and you send by Brownian motion from infinity another particle until it sticks, and so on and so on. And then you have a tree-like structure. And now what happens with the delay, that it's a fractal structure, but we don't know we don't know that it's fractal. There is no theorem. There is only estimate on one side by Harry Keston. So there are more than 1,000 papers, but only one theorem by Harry Keston that it's fractal on one side, but theoretically it can be space filling. So he proved that it's not a straight line, but theoretically it can be space filling. In the plane or in the space, let me just see. The plugin is not installed. Okay, plugin is not installed. Okay. Yeah, it will take 1 second now, because here in Mozilla the plugin is installed. Okay, very good. Yeah. So what happens, let's say, if we grow slowly, so there is one thing which goes from infinity and then it attaches, then there is another thing which goes from infinity, it attaches, etc. Now it grows and grows and grows. So the relation with this, that there were a few papers by physicists in 90s, which said that this is described by conformal field theory with center of charge 0. Then they retracted, and these people who written this paper said they never wrote them. Those were imposters, so it's not conformal field theory. So the current state of the matter, we don't know whether there is a fractal object there or not. So what we know that it's not a straight line, that was Harry Keston proved, so dimension is strictly bigger than 1, we know that it's bigger than 4/3. We cannot prove that the dimension is smaller than 2, we can prove that it's space field. There is no continuum object there, because if you define continuum version of this with the Brownian motion, etc., you run into something Hellish type, which is ill-posed. So, of course, on the level of abstract compactness arguments, there is a continual inversion, because here you get a random compact of some diameter, you rescale it to diameter 1, you send measure of the lattice to 0, by subsequences you will have some random compact. But maybe this random compact is the whole disk. Okay, then you can do something different. You can look at the branches of DLA. So you look not at the random compact, but at the random structure of paths inside. Then you get some random structure of path in disk, which still might be non-trivial. So Benno and Mandelbrot thought that you should not, that it doesn't have a nice limit as a compact, but as a mass distribution it does. So you should look at distribution of mass, and then it is fractal, whereas as a compact it's likely to be space-filled. So it's, I think, it's wide open, and it's probably not related to what I said.
So that even that is not
Even that is not, it's not completely clear that it's not related, but I think the current understanding is that it's not related. It's very tough to prove that dimension is smaller than 2. It's incredibly tough. It's the same for self-harmonic walk. It's not known the dimension as 2, that it's not space-filled, that there are holes. If you look at the pictures of different sizes, there are on the internet, you can find up to 10 billion. It's not clear that they're self-similar. They might be changing with the number of particles, and the holes might be getting less and less. But as a mass distribution, it's not space-filling, I think. And that's what Mandelbrot said. He actually said that there are two fractal structures on the structure of the diameter, and I think diameter to some fractional power is square root, and maybe this is the inner one which one should look at. But I think he put it in writing, you can find it somewhere. But he had some interesting ideas.
More questions?
Yeah, sorry. So for SLE, it's not proven that it's symmetric for cases other than.
No, it is proven, but not via the correlations. It's proven, for example, as I said, from percolation, it's clear that the interface from A to B and from B to A is the same. So SLE6, which describes percolation, is symmetric. So it was for a while open conjecture for about 7 years that SLE is symmetric because no one could prove it. We still cannot prove that the correlations are the same because they satisfy different PDEs. So we cannot show that these PDEs have the same solution. But it was proved by another method of you grow simultaneously DLA from two sides and you couple them in some way. That was proved by Zubedai and Zhang. Well, rather by Zhang and Zubedai. For SLE. No, for DLA there is internal DLA where you chip off from the interior of the boundary, which is completely analyzed and which has something to do with free field and with all that. But this DLA I don't know. But it's really a beautiful problem, and I thought how on earth can it be difficult to prove the dimension smaller than 2 until I thought about it for 2 weeks. It's difficult.
Questions? Okay, so my understanding is that this problem of invariance, of conformal invariance, the main progress happened in hexagonal lattices too. So,
for percolation, yes. For Ising model, we can do with any lattice. Ising model essentially we can do any what is called as a radial graph. It's a graph where all faces are inscribed with circles of the same radius. So in particular, hexagonal square lattices would do, but it's a much wider class of graphs. So for example, the row stylings also fit in, and there are some random graphs which fit in. For its specific thing about percolation, so there is this central charge parameter C or kappa parameter, which is related to 60 degrees for percolation, and there the symmetry helps a little bit. But other model, for all other models, it's all the lattices. All the lattices. Just for percolation, it's a bit embarrassing. You can only do hexagonal lattice.
These questions have natural extension to 3 dimensions.
Yes.
And what is the schematic suppose that it's not completely empty or something?
So the physics intuition about dimension 3 is that everything qualitatively is the same. You have phase transitions in all these models, and you have some exponents. So I must say here that for every model there is a critical dimension after which it becomes much easier. So for Ising it's 5, for percolation I don't remember, so for Brownian motion it's 4. So for example, for Brownian motion after dimension 4 it's essentially a simple curve, doesn't touch itself. So self-harmonic walk from dimension 4 onwards is an easy object. But for almost all models mentioned, dimension 3 is still a difficult one. And the understanding is that qualitatively it's exactly the same as dimension 2. But you don't have rational exponents and you don't have integrability or exact solvability. So that's the physics understanding. Now, here we really use conformal maps. if you ask what can be transferred from what we learned to dimension 3, actually there are some things, if you look really carefully, which one can try to use, because mostly we speak not about conformal invariance, but about conformal covariance. In dimension 3, in principle, you can expect covariance under some group of diffeomorphisms, so in principle, you can try to work this. Another thing that we get here, say, some correlation which satisfies, for example, Laplace equation, which is a harmonic function. Then we map to a disk, solve it, map it back, everything is nice and easy. Now assume you have a model in dimension 3 that you get something which is discrete harmonic in some domain. You can't map this domain to a sphere. Even if I give you some non-trivial domain like a tetrahedron, and function is harmonic with given boundary data, you can't write a formula. So what can very well happen is that you prove, and there are some, for example, uniform spanning tree in any dimension is related to harmonic functions. So what will happen, say, with the uniform spanning tree in dimension 3, you can relate to harmonic functions, but we cannot deduce dimensions from that here. It might very well be that the dimensions you will write, the dimensions are related to eigenvalues of Laplacian in three-dimensional ball with some boundary data, which you can calculate exactly, but it will be as good an answer for us. And also the other possibility is that for models, I hardly believe that an Ising model in dimension 3 would have harmonic functions, but it might very well be that you have some generalizations of discrete analyticity. In dimension 3 there are several different generalizations. Or it might very well be that you should look not at function of one point, like you do in the plane, but of a function of a curve. In the plane it makes no sense, in plane is the main sort of, but in dimension 3 already a curve starts playing a role. So for example, if you look at the generalization of Cauchy-Riemann equations, so Cauchy-Riemann equations have a point singularity. And their generalization in dimension 3, they have two sorts of kernels. One has point singularity, another has loop singularity. And this actually has to do with my first exchange with Dennis. So maybe it has something to do with this problem as well. So maybe you have to look not at the function f of disorder operator at a point, but f of disorder operator on a loop. So in principle, it might be that the similar techniques will apply to dimension 3, but they will never give nice answers, like 91 or 48. You would get some transcendental numbers. So it might be that it's not as bad as we think.